0. So basically, they're saying that suppose a machine starts oscillating due to transient stability analysis. So the first point and the second point, if it swings between these 2 points, between the final steady state point, this area and this area will be the same, right? So basically what happens when the fault happens, fault or any situation happens, there will be an acceleration or a deacceleration, which will cause the machine to go from the current point to this new point, right? But when it comes here, it wouldn't stop because due to inertia, it will keep on going to the point where the effect of inertia is nullified. But then this will create a reverse acceleration and will swing back. So it will oscillate for some time before settling at the new point. It's more or less like a pendulum, right? So how is this aiding us in transient stability analysis? So if you are looking at the area between, so there are 3 points. What is the first point? It is the initial condition. Second point is the new point or the new stable point, which is corresponding to the new condition, and this is the maximum. So the area between this one is A1 and the area between these two is A2, right? So if A1, so by equilibrium criteria, we can say if the system is going to be stable or unstable. If A1 is less than A2, it is stable. A1 is equal to A2, then it is really stable. And if A1 is greater than A2, it is unstable, right? So far, so good. Okay. So let's look at what are the applications of equilibrium criteria. So the first one is we can do sudden. It's basically a permutation and combination of the power components, right? So sudden increase, sudden mechanical input increase, right, of generator, synchronous generator, right? Then sudden mechanical load increase of synchronous motor. It matters that it is a synchronous motor, right? Then removal of a transmission line by fast acting circuit breaker. Right? Then short circuit, we have a short circuit in the middle of the line. Then like these are all different combinations that we can see. Short circuit near bus bar and finally circuit on bus bar, right? Okay, right. So that is the applications of equilibrium criteria. So we will look at 2 of them, right? Rest I'll give you the notes. You can go through the notes because the approach is almost in all cases the same. So we will look at the sudden mechanical input increase of a generator and probably the short circuit in the middle of the transmission line. Rest is, give me 1 second. Hello.
Hello, good evening.
Good evening.
My name is Lakshmi Bhai.
Yeah.
Yesterday, uncle gave me your number, so I just wanted to get myself introduced and speak to you. Is it okay to talk now?
Can I call you back in 2 hours? Because right now I'm in the middle of a meeting. Is it okay if I call you back?
Okay.
I'll call.
Yeah, you should just give me a missed call. I'll give you a call back.
Okay. I'll give you. I'll send a message on this number, or I'll give you a call on
Yeah,
this number.
WhatsApp number also you can give. Can I have your name if you don't mind?
It's Adib. ADHIP.
Adib.
Yeah. Right. So
ADHIP.
yeah, ADHIP. I'm really
Thank you
sorry
so much.
because yeah, I'm in
No,
the
no,
middle.
no. I can totally understand. I can totally understand. You can just ping me. Thank you.
Sure. Bye.
I'll wait for you.
Yeah.
Take care. Bye bye.
Yeah. 2 hours. I'll call you by 7:30 my time. If that's okay.
No problem.
Yeah. Thank you. Am I audible? No. Okay. Thank you. Okay. So right. Okay. So we will look at what's happening. Okay. Yeah. So we will look at a few of them, and rest. I'll give you the notes as well, right? So you can have look at those notes. So this is something that I keep on telling you whenever we are studying a method or any formula. Ask what are the assumptions, right? These are important because if you tweak the assumptions, the method will change. So first assumption is that the point where acceleration is equal to 0 and omega is equal to omega s is considered as a stable point, right? And pa is equal to 0, but we suppose there is no acceleration, but this speed is not synchronous speed, or there is acceleration but speed is synchronous speed is considered as a point, right? And the third is right. Is this clear? Is this clear? So far so good. Okay, so let's see the first case. First case would be just out of curiosity, wanted to know what kind of devices do you use to attend these classes? Are you guys using mobile phone or laptop or computer or desktop computer? Nice. Cool. I just wanted to know like if it's I've asked this earlier, but right. right? So we have a generator connected to an infinite bus via a reactance, right? So let's say that this is the PS1 is the initial mechanical input and PS2 is the new mechanical input, and based on the condition that we are assuming, PS2 is greater than PS1, right? So when PS1 was the mechanical input, there would have been an electrical output. What would that be? It would be EV by X1 equivalent in delta 0. So we are marking the initial delta as, so this is our PM1 in delta 0, right? So this is our initial output, right? So what happens now? PS has changed. So when PS changes, so when PS increases, PE also will increase, right? So in this given setup, EV and X don't change. The only thing that would change is delta. So there is a new PE2, which is EV by X1 equivalent sine delta, or this is our delta. So since we are not looking at the condition where there is a fault or a network change, PM1 would be, can I move on to the next slide? Okay. PM1 would be equal to PM2. So let's look at the graphical setup of this. That is a fairly decent size, right? Right. So so this is our initial condition. So this is our PS1. So this is P versus delta, right? So this is our PS1. So what would this be? Be our delta 0. So suddenly the mechanical input now increases to PS2, right? And this would be our new delta, right? And say suppose this would swing up to this. So this point is over, this point is A, and is E, and this point is, and this is the area that we are interested in. Right. So this area is A1 and this area is A2. And now I hope you guys have a visual aid to picturize the equal criteria, right? So the synchronous generator is supplied with a mechanical input of PS1, and corresponding to that there will be an electrical output PE1, right? So this one will be equal to PE1, right? And this is shown as point A on the curve, right? So the mechanical input is suddenly increased to PS2. How do we do that? Mechanically, we open the turbine valve, right? But the electrical output will not change instantaneously. This would change instantaneously, but this won't change instantaneously due to moment of inertia, right? So what will happen? We will have E is equal to the new mechanical output, but at the instant of change, it would be electrical output would be same. So that would be PS2 minus PM1 sine delta 0. So what would this be? This would be positive, which will cause acceleration, right? So the extra mechanical input is stored in the form of kinetic energy of the rotor due to acceleration. And at this point, what will be the case? Omega will be greater than omega s. So I will create a table over here that will help us understand what is happening. So this is our point. This is the power relation. Right? This is acceleration. This is with respect to omega, and this is rho max. Right? So let's look at what happens at point A. Right? So what is point A? It is the point where, so this is just before the output changes, right? The mechanical input changes. So at this point, it is P is equal to PS1 minus PE1, which is 0, right? At this point, the system is stable. So either it is neither acceleration, deceleration is equal to 0. It's neither acceleration nor deceleration. And what will be the speed? It would be synchronous speed. So what kind of a point it is? It is a stable point. So if you leave the system at this point, it will continue to be at this point without any change, right? Now what is going to happen? Suddenly the mechanical input changes. So it has to transition from A to B, right? So what is P right now? Mechanical input has already reached PS2, but the electrical input is still PE1, right? So this would be positive, and this will cause acceleration. And what would be omega? Omega would be greater than omega s. So what will happen? Delta will increase, right? Is this clear? So basically what happens when it is going from A to B, the mechanical input is always greater than the electrical output. So it will cause acceleration, and omega will be greater than omega s, and delta will increase. Yeah. Right. Now what happens? It will go up and it will reach the point B. Right. Now when it reaches the point B, what happens? E is equal to PS2 minus PE2. This would be 0. So no acceleration, no deceleration. Right. So it is similar to A, but it is not a stable point. Why is it not a stable point? Because omega is not equal to omega s, and omega is equal to max. So due to this acceleration, omega would have reached its maximum value now, right? And it is following me, right? I just hope you guys are following me. So this is clear, right? It's very straightforward. It's more or less like telling a story, right? And so this was one of those combinations we saw. If the acceleration is 0 but omega is not equal to omega s, it is, what is this? It is a swinging point, right? What will happen? Delta will increase due to moment of inertia. Delta will increase due to moment of inertia. So now, right now, the accelerating factor is, or the thing that is driving the uh, rotor or the delta is now moment of inertia, right? So now what happens? It will keep on increasing, but at this point, what is P? It is PS2 minus P2, the new value, right? That would be PS2 minus PM sin delta, and this value is going to be greater than this value, right? So now what is happening? It has reached here, but now due to moment of inertia, it is keeping on increasing, right? So the electrical output will be greater than mechanical input due to that swinging. So this would be negative, right? So what will that cause? It will cause the deceleration. So basically, it accelerates up to this point. Then from this point, it starts deceleration. The acceleration is maximum over here. Then slowly the acceleration comes down, but due to moment of inertia, it will keep on swinging, and then the deceleration keeps increasing. Right? So omega now is going to be less than omega max, but omega will still be greater than omega s. So there is a deceleration, but speed is greater than synchronous speed. So delta will further increase, right? Can I move on to the next slide? now it will go and it will reach the point C, right? What happens at C? What is the factor? It is P is equal to PS2 minus PM sin delta, which is negative, right? So it will cause deceleration. But what is omega? Omega will be omega s at this point. So again, even though omega is equal to omega s, there's a deceleration. So this is going to be a swinging point. What happens? Right now, omega is equal to omega s, and there is a deceleration. So what will happen at this point? Delta will start reducing, right? So at this point, omega is equal to omega s, but there is a deceleration. So delta will start reducing. So you are going to start swinging back. Omega will become less than omega s in the next. So now it is again, now it's going to swing back to C to B. Right? Again, when it's swinging back to C to B, P is going to be same, PS2 minus PM sin delta, which is still above PS2. This is going to be negative. So this is going to be deceleration. But here right now, omega will be less than omega s, right? So delta reduces further, right? Then it comes to the point B again. At this point, what happens? P is equal to PS2 minus PE2 is equal to 0. So neither acceleration nor deceleration. PS2 minus PS2. Thank you. Neither acceleration nor deceleration, but omega is now omega min, which is less than our singular speed. So this is going to be a swinging point, right? So this again will continue due to moment of inertia backwards, B to A. So at this point, what happens? P is equal to PS2 minus PE2, which will be positive. So there is acceleration. So omega will start increasing, but omega will be less than omega s. So delta will keep decreasing. Right? So now what happens? Once you guys have finished noting this down, right? Okay. So now let's see what we are trying to say over here. Right? Right. So okay. So basically the system starts oscillating. So suddenly the mechanical input increases. So there is an acceleration. Here the omega was, what was omega at this point? Speed was omega s, right? Now it, due to this sudden increase, this will go omega s plus, right? Omega s plus means it is more than omega s. So it will go beyond omega s and will come up to this point where it will become omega max. Right? Now it will start, it will go due to inertia, it will keep on going up, but it is going to be deceleration, but omega will be still omega s plus, right? Then we'll come to this point C, right? Due to deceleration, where it will again become omega s, right? So basically, it will become omega s over here. Then it will further start reducing. Then it will become omega s minus. Then it will come to the point B where it will become omega minimum, which is also less than omega s. Then from this point, when it starts swinging backwards, it will start becoming omega s minus. Then it will come to a point where this is omega s minus. Then it will come to this point where it is again omega s. So basically what happens is that it will just keep on swinging in such a way that finally you come to this point after 2 or 3 swings where at B the speed becomes omega s, and PS2 will be equal to PE2, so there won't be acceleration and it will become a stable point. So basically stable point, swinging point, swinging point, swinging point, swinging point, swinging point, swinging point, finally stable point, and it will stop. Is this clear? Okay, good. Right. So now let's see how the stability criteria can be measured using this one. Right. Now assume this is our PS2 and this is our original PS1. Right. Suppose it swings up to this point now. This is A, point is B, and this point is C. Area is A1, this area is A2. So the condition where omega is equal to omega s is achieved, or the point where the deceleration becomes zero, or means the omega becomes omega s is achieved in the first swing. It is such a way that A1 is less than A2, right? Then it is stable. This is our delta max. So if you see over here, even though the angle goes beyond 90 degrees due to the swinging action, we still have some chance of stability. So during the oscillation, the angle can go beyond 90 degree, but it should not stop there. So the idea is that this point B, right, the final settling point B should not be, can go beyond this, but it should be such a way that it keeps. Yeah, my check. Am I audible? Right. Okay, good. So this is a stable condition. If A1 is less than A2, it is a stable condition. Now small sine wave, pardon, small sine wave. The condition where A1 is equal to A2. condition where A1 is equal to A2. If A1 is equal to A2, then this is really stable, right? So this is our delta 0, delta C, delta max. So this is called as critical clearing angle. So this is extremely important with respect to a fault. Say suppose this was the system operation point and a fault occurs and the system starts swinging. If you don't clear it by this point, right, if you don't clear it by this point, then the system will swing out of control. So this is the minimum angle by which you have to clear the condition such a way that the area is equal. If you clear after this point, A1 will be greater than A2 and the system in the oscillation will go beyond this point and will go out of control, right? So here what happens at this point, dou delta by dou t will be exactly 0 at this critical clearing point, right? And here at this point delta 0 delta max should be dou delta by dou t will be less than 0, which is still fine. Now the last condition is when the fault clearing point or the stability point is such a way that it is beyond recovery. Suppose this was our initial, okay, now say suppose, so this was our initial operation, then we increase the mechanical input to this point ES2. As you can see, even up to this point, it's taken as area 1, 0, this is A1, this is A2, right? So in this case, A1 will be, sorry, A1 will be greater than A2, right? In order to maintain the stability of the synchronous machine, the actual angle of the rotor during fault should be less than the critical clearing angle. So suppose if this condition happens, then at this point, d delta by dt am I audible? So just to give you a brief summary, so synchronous motor is also more or less the same, which I want you to try, right? The only difference with respect to a motor and a generator will be we can just map it the same way. Mechanical input output increases, decreases, right? So this is synchronous generator, synchronous motor, right? The difference is that here A1 is less than A2 is stable. In both cases, A1 less than A2 is A1 is equal to A2 is equal in here, and A1 greater than A2 is stable. Is just the mapping of the input and output changes, right? Here what is P? P is equal to PS minus PE. Here it would become, only difference is that here P is PE minus PS. Clear? Okay. So now let's look at the condition with fault in the middle of the line. For this, I'm just loading the other node. Give me a second. Because this requires 3 sine wave, which I'm not good at drawing. If it was a board, it would have been easier, but unfortunately, it's not a board. Yeah, these are different. In this node, there are different, all the different conditions are, I have written down all the different conditions. So this one I'm telling you, I want to discuss because this actually has a 3 sine wave scenario. Is this visible, guys? Is this clear? Is this visible? Okay. Right. So this is the system that we are considering. This is like a fault in the middle of the transmission line. So what is happening? There is a generator, right, which is connected to a bus bar via a reactor. Then there are two parallel transmission lines. Then it is connected to the infinite bus bar via another transmission line. So now the condition that is happening is that a fault is happening in middle of one of these transmission lines, right? So if let's assume PS is the initial is the mechanical input. So the mechanical input of the system does not change. That's what we are assuming, right, at this point. So PE1, right? What is PE1? PE1 is the power that is was transferred. So this is the curve. With, why do we have three curves? Because in each situation the network is different, right? So in the first case, it is these two in parallel, series to these two, right? Then what happens? A fault happens over here. So this will become a delta, which we have to convert into a star, and that star will be in combination with these two, right? This will become a star that you have to convert into delta. Then that conversion we will see. There is another problem, right? So that is another network condition, which is a reduced network condition. And finally, when the fault is clear, this transmission line goes away. So it is going to be just these three series. So the electrical power curves, which is PM equal to EV by X divided by X. So EV divided by X sine delta, right? So EV by X, which is PM1, will change for all three conditions. So that's why we have three curves, right? So it's basically how do we track the area, right? So before the fault occurs, this is the point A, right? Say the point A is there, and now the fault occurs. When the fault occurs, the network condition shifts, and the operating shifts to this curve. Suddenly shifts to curve, this one, this curve, which is PE2, right? This will shift to PE2 and to the point B, right? And at this point, what happens? The mechanical input is greater than the electrical output, so it will cause acceleration. So it will increase, 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 increase. And at this point, what happens? At point C, the fault gets cleared. When the fault gets cleared, the network configuration changes again, which will cause the power curve to be on this curve. And at this point, what happens? At this point, even though the fault is cleared, there is still, and there will be deceleration because the output is more than the network condition. So input. So it will start oscillating and it will oscillate and finally settle at this point. So this has to be fault has to be cleared by this point. This has the critical angle. So in order to find the point where the critical, so we find what the area is this one, and the condition where this is matched, that A1 is equal to A2 is matched, will be the critical clearing angle, right? Is this clear? So let's use the equal area criteria to see how it works, right? Oh, yeah, let's derive the condition. Oh, you want me to repeat it? Okay, wait. So the system is operating at point A, right? Now a fault occurs which causes the network configuration to change. How will the network configuration change? Because suddenly there is a ground connection which causes the total network impedance to come down. So effectively the operating point becomes B, right? And due to the fault, the effective electrical output also reduces because all the power does not go to the load, right? So this will cause the system to accelerate, and this acceleration happens. And at point C, which is our critical clearing angle, we will clear the fault, by which we have to clear the fault. When we remove the fault, the new network it won't go back to the original curve because the new network does not have one line, so it will go for a intermediate electrical output characteristics and come to the point D. At this point, usually if there was no moment of inertia, the system should have settled at D. But what happens, due to the moment of inertia, there is a deceleration. So it will come to this point, it will uh, at this point omega will become equal to omega s, but there will be deceleration. So it will oscillate between these 2 points and finally settle at point D. Come and settle at point this one, where mechanical input and electrical output are the same. So it will come and settle at this point, right? Is that clear? Okay. So yeah, this will become more clear when we actually apply equal area criteria, and let's see how that turns out, right? Right. So how do you calculate area of the curve? It is, you just integrate it, right? Delta max. This is what equal area criteria says. That for the critical clearing condition, this will be equal to 0. So, and what is this? This would be delta 0 to delta C A into d delta plus delta C to, you can split it at the critical angle A d delta would be equal to 0. Now what is this between this point? It would be delta 0 to delta C mechanical input minus EE2, right? So this is the fault condition. D delta, and what is here is delta C to delta max. From the clearing point it is PS minus P E3 to 0, right? So now if we further substitute, what would that be? Delta 0 to delta C PS minus M2 delta. Is this mathematical expression clear? I think it should be straightforward, right? Shall I move on to the next slide? So if we do the integration, what will we get? We will get PS delta plus EM2 cos delta 0 to delta C plus PS delta plus EM3 cos delta C to delta max is equal to 0. So if you substitute and you will get equation like this, that PS into delta max minus delta 0 minus EM2 cos delta C minus delta 0 into EM2 cos delta 0 plus EM3 cos delta max is equal to EM3 minus PM2 cos delta C, right? So So if you rearrange this, you will get the critical clearing angle as cos inverse yes are you done copying this down? Okay. So now let's look at what will be delta 0 and delta 1. So what is the condition for delta? It is PS is equal to E1 is equal to EM1 and delta 0, right? So what is delta 0? Delta 0 is equal to sine inverse PS by what is PS will be always less than PM, right? Or it will be always less than or equal to PM. So delta would be less than or equal to 90 degrees, right? Now similarly, what is delta max? Right? It is PS is equal to E3 is equal to EM3 sin delta max. So delta max would be equal to sine inverse PS by EM. This also will be less than or equal to 90 degree, which is why it is stable, right? It also can happen such a way that mm, delta max can go beyond 90 degrees. So there is a possibility that when you're taking sine inverse, it can go beyond 90 degrees. So if it goes beyond 90 degrees, it is basically PS is equal to M3 into sine of 180 minus delta max, right? So sine inverse of PS by PM3 will be equal to 180 minus delta max, and this means this is if the operation point is beyond or near to 180 degrees. It's greater than 90 degrees. So this condition.
You are currently the only person in this conference.
So we will follow this equation. If we write it down, we will have delta 0 is equal to inverse PS by PM1 and delta max is equal to 180 minus inverse PS by the only one here. How is it? Varun Thakur, I'm audible, right? Right. Okay, audible now? Is it audible now? Hello? Just let me know if I'm audible. Right, I'm just typing it also. Show file. Oh, hello? Hello, let me just mute and mute. Now? Am I audible now? Varun? Okay. I think I'm audible now, right? Okay, so let's try a question. Okay. So the condition is asynchronous generator is connected to infinite bus bar via double circuit line, right? It was delivering 1 per unit power initially and a fault occurs what are the initial max and critical load angles given following power profile. So you are given that initial power transfer is 1 per unit, right? That is your PS. You are given PE1 is equal to 2 sine delta 0, right? PE2 is equal to 0.2 sine delta. PE3 is equal to 1.5 sine delta. Can you guys solve this or do you need help? So you are asked to find delta 0, delta max, and delta C. Okay, good. Okay, del 0 is 30 degrees. Got it as 30 degrees. Is it good? That is 30. Right. And del C. Yeah, that is a huge calculation. That's fine. Yeah. Varun, I hope you also got these answers, right? If you are having any issues, let me know. I will solve this for you. Good. So you can do the calculation. I think the answer will come around 62.5, I think. You can leave a space, you can come back and do the calculation. Comes around 62.5 degrees, right? Okay. Okay. Let's look at the next question. We are given these values. PS is equal to, I'm just going ahead because I just, it's just time constraint. You can leave space to do the calculation, right? Or we can do this one also, 1 point. So in these questions they are giving you PM1, PM2 values, right? But sometimes they won't, right? So yeah, here they have given you cylinders. Can you guys try this? So the question that I would ask you first is, do you know how to calculate PM2 and PM3? If you don't know that, then this will be tough. If you have an idea on how to calculate that, just think about what the formula is for these two, then you will be able to calculate, right? Are you guys going to try this question, or do you want me to solve it for you? Okay, good. Did you guys get the answer? Did you calculate, just let me check it. What did you get PM2 and PM3 as? These are the first steps, right? Did you get these values? Okay. Varun, what about you? Okay. What did you do? So, what is PM1? PM1 is EV divided by 1 equivalent. What is PM2? Is EV divided by 2 equivalent. What is PM3? It is EV divided by 3 equivalent. So you are given PM1 and PMX1. So you can calculate product of EV as 1.73 into 0.72, right? So you will get that as 1.245. So what is PM2? It is 1.245 divided by 3. So you will get it as 0.416. And what is PM3? It is 1.245 divided by 1. Right? Is that clear? And now this with these values, can you calculate delta 0 and delta max? Okay, correct. And if you try to now, if now you have all the values, do you want to just try and calculate delta 0 for delta c? Yes. One, point, okay, one more thing, you have to always substitute this in radians. Okay? To find this properly, you have to substitute this in radians. About 126 degrees in radians, that in radians. No, it will work, I guess. No, it won't work. You need to do that in radians. So, see, 0.1 minus If you got that answer. What's happening? Are you guys getting this answer? Okay. Do this one because I'm giving you the time to do this because you need to get a feel of this. Are we good? Sure. Okay. So means like the formula that you substituted is the same, right? Or is there some difference? Okay, so you have to make sure that see, I even though I wrote cos 0.61.4 and cos 2.21, this is in radians. This is not in degree. This is same as cos 35 point something, and this is cos 121.21. Okay, make sure your calculator, if it is in degrees, you can always substitute this as cos 5.26 cos. Be always be very careful about what is the unit. Yeah, Varun, what about you? Right. So sometimes what happens is that they will ask for critical clearing time also in. So we found the critical clearing angle. Now we have to find the critical clearing time. Like time, we can't always say this is the angle, right? So the tangible quantity that we measure is always time. So how do we find it? So there's a small derivation. So we are going to assume that the electrical output is completely zero. That's the solid short circuit fault, right? Just for the sake of the derivation. So if we integrate it, dou delta by dou t will be Ps divided by m e. We integrate it again, we will get it as Ps by t square plus a. So what is t? We have to find the time taken for clearing the critical angle. So delta c would be Ps divided by 2m Tc square plus. So how do we find a? So we will substitute the initial condition, right? So when the t is equal to 0, what is delta? Delta would be delta 0. So if you substitute that, you will get a is equal to delta 0. So what is delta c? Is ps divided by 2m c square plus delta 0. So if you rearrange, you will get tc is equal to square root of 2m delta c minus delta 0 divided by this, right? Is this clear? This also is done, right? So let's look at a question. Can you guys solve this question? Let's see what is given. You have to be careful about what is given, right? Given. What is PS? PS or the mechanical input or the original value is? What is PS? Question. You can do the question, but just tell me so that I know that you guys are not taking the wrong values. What is PS? PS is given as 1 per unit. Right? Then what is PM1? Maximum is given as so, and what is PE2 and PM2? This is a solid short fault. There is no output, so it becomes 0. Right? And finally, what is PM3? Again, the fault is cleared, so it goes back to system. So if you're looking at the system curve, right, this is the system operating condition. Right? Fault occurs, the output becomes 0, and the fault is cleared. It goes back to same curve, right? So what will be delta 0? Will be inverse is divided by P. Are you guys going to do this problem? I'm just going to try. Give it a try. Yeah. Good. You guys know what? Do you guys understand what all things that you need to do, right? Varun, are you there in this call right now? You got del 0 is 23.57, yes. And what will that be in radians? Because for the critical clearing angle, you need that in radians. So convert that into radians and tell me. This is 23.57 degrees, and that is correct. 0.41 little max. to correct. We will get this as I think 150.41 degrees or 2.73 temperature readings. Right. Now can you calculate delta C? What is delta C? Cos inverse 1 into 0.72 minus 0.41 minus into is 0 matter 1.5 of got the answer. Basically, what are we saying? So the fault occurs, it goes 0 and it goes along this line. So by the time it becomes 90 degrees, by the time it becomes 89.3 degrees, we clear the fault, system will go back to the normal operating condition. Otherwise, it will swing out of synchronization. 1.56, okay. Yeah, I think I made a mistake. Then you guys did not correct me either. Not fine. Becomes 89.57 degrees. That's also okay. You can put it in radians, but in your calculator you have to put it as, it should be cos. My bad. Should be so this is the answer. So to be careful about your calculations. Now let's do TC. What is TC? This is 210 into delta C minus delta 0 divided by this. What is given as 2 into is n, and we have to calculate, right? We are given h, it is in h divided by, since we are taking these angles in radians, you have to take it as pi f. If you are taking this difference as degrees, you can substitute as 180f. It doesn't matter. You have to be careful about what you're doing. Right? 1 into we'll get it as 0.038. 0.038 into, then taking as radians, I'm going for radians value. Right? H value we are given the question, right? Inertia constant. What is H? H is the inertia constant, 6 mj by mva. That's okay. That's okay. That's okay. I'll give you one more question from the concept of inertia constant. Have you guys taken this down? We'll do one more question and then we'll proceed to the next topic. Can you try this question? Okay. So these are all questions that are looking for your fundamental. So try to remember what the inertia constant is. Okay. Varun, are you trying? So you basically have to understand, to solve this question, you have to recollect what inertia constant is and what swing equation is. It's very straightforward. It's a small multiplication. Did you guys get it? Right. What is H? You know what the formula for H is? Look at what all parameters are given, and it is basically kinetic energy stored divided by rating of the generator. So you are being asked to calculate kinetic energy stored. What is kinetic energy stored? Basically, H into this. You have 8 into 8 millijoules per MVA into 100 MVA. You get. Did you guys get this? Rushing you because we have to. The next one. Did you guys find the acceleration? What did you get alpha as? Good. Good. So basically PA is equal to into alpha. Since they are asking you for degree per second, how do you calculate m? Is equal to sh divided by 180f. You can calculate as 100 into 8 divided by 180 into, you get it as 0.88. So alpha is equal to divided by, substitute, you will get this as 80 minus 3 divided by 4. You will get this as 337.5 electrical joules per second square. So had they asked for radians per second square, you would have used pi f over here. Is that clear? So next thing that we are going to look at is methods to improve transmissibility. So what are we trying to do? We are trying to reduce the time for acceleration, hence reduce the oscillation, right? So when a short circuit fault occurs, the electrical output, so basically the bigger issue that we are facing is short circuit fault. The electrical output reduces, right? When short circuit fault and electrical output reduces, and the synchronous machine will experience acceleration, right? So if the acceleration period is high, if it takes a lot of time to accelerate, then what will happen? The acceleration area, which is a1, will be greater than a2, and the machine will be unstable. So if we have to reduce a1, we have to do either of the two things. The first one is reduce the acceleration or reduce time for acceleration, right? So we have two approaches. So the first one is, the first method that we can think about is selection of m value. By selection of m value, what is alpha? Alpha is E divided by m. So if m is higher, alpha would be lower, right? So for the sake of transient stability, we always prefer to install larger capacity generator. But again, this will have a big issue with swinging together, and if one generator goes out, what happens? So in terms of system design, we usually tend to have smaller generators, but this is one approach. Second one is to control the speed of operation of CV. So what happens? Speed is inversely proportional time. The higher the speed, lower the time taken, right? So what happens if the speed of operation is high and the time taken will be low, then the fault will be cleared quickly and the area A1 will be, right? then we can always install good governors. So basically, so we always assume that PS is constant. So here what we are trying to do is we are trying to play with the assumptions. We always assume PS is constant. So if we have a really good governor, right? So when the fault occurs, PS also can be reduced. So PA is equal to PS minus PE, right? So if PS can be reduced, this also will be reduced. So if you are having a really good governor, it can adapt pretty quickly with respect to the fault. And so nowadays what happens is we have speed governors that are based on electronic devices so that it's faster. Okay? Then the fourth option that we have to increase the stability, which is same as what we saw in steady state stability also, is the we can install series capacitor. So this is one important fact. Both steady state stability limit and transient stability limit can be improved using series cap. Very important factor. Last but not the least, we can always have the excitation control. So the nature of SC fault is basically inductive. So the SC fault current is also fault current will also be inductive in nature. That means it will lag behind the voltage. So which reduces the generation voltage due to armature reaction. So this will cause generation voltage to reduce due to armature reaction. So if we change the excitation of the rotor, what will happen? The effective voltage will increase and the steady state, the transmission, that EV by X, right? So if you change the excitation, this E can be increased, thereby increasing the operation or transition limit, right? See, suppose now we have a unsymmetric fault or unbalanced fault. How do we improve? All these are the assumption it's a symmetrical fault. Now if you have an unsymmetrical fault, right? The first one is single CB operation. Even though this is actually not recommended, but this is actually a very safe option. So what happens? So an unsymmetrical fault is more like a line to ground fault. Line to ground fault, as we have seen, is the most severe fault at the generator terminal, right? So what we'll say is that we will just take out that one pole operation causing, so each pole has separate, each phase has separate circuit breaker which operate in tandem, right? So here we will just open one of the phases, even though it will cause unbalance, but it will clear the fault immediately, right? Second one is called as dynamic resistance switching. Suppose what happens is that for in case of dynamic resistance switching, what we do is that at the generator bus, right, we have a circuit breaker, we have a bus. So this is where the, suppose fault is happening. So what we do is we actually have a switchable resistance at this bus. So what happens when the fault occurs? We will switch on this and we will have, it will be PA. In this case, it will be PS minus PE2 plus square R, right? So suddenly the effective acceleration, when we have a fault, we will dynamically switch on the resistance, and this will cause the effective PA to come down. So usually what happens is that this is where we have the importance of neutral grounding comes into picture, because in this case this Rn will act as the dynamic resistance, right? Right. So there is a thumb rule whether to choose resistance grounding or reactance grounding, right? So if for the generator x0 by x1, zero sequence impedance divided by sequence impedance. If it is less than 3, then we go for then we go for then we go for ground. Right? Are you guys with me so far? Right. So I think we have, in the major topics that are left, we have to look at protection, that is few terms in protection, how a circuit breaker and the relay work. Then we have economic load dispatch and load frequency control. So this will take me around 2 more sessions, right? And hopefully we'll wind up. So before we wind up for today, I think I'll give you one more problem, right? We will see one more problem. Is that okay? I think we have 10 more minutes, so we will see 1 or 2 more problems. Can you do this question? Go ahead and try. I'll give you 3 minutes. I'll give you the options. It will be easier. Option A. Okay. So this is Varun. Takura. So we have to calculate alpha is equal to PA by M, right? So what is PA? 25 minus equal to 25 megawatt, right? Now what is M? We are asking in degrees. It is SH by 180 F. Right? What is S? They have given us 100 MVA plus 10 MJ plus MVA divided by 180 into 50. So I think you will calculate this as 0.111. So what is alpha? 25 divided by 0.111. You get it as 225 electrical degrees per second square. But if you see in the question, I have asked you for mechanical degrees. Option 1 is not the correct answer. That's what now you got it as 0.21, right? But this is wrong. So you need to convert this into mechanical degrees. How do you convert this into mechanical degrees? Electrical degrees is mechanical degree into multiplied by 2 by p. Alpha value 25 divided by 9111. 225 point. Yep. 225 point. How did you get this? 100 into 10 divided by 180 divided by 50. Did you get MS 0.111 or this is basically 1 by 9? 1 by 9. Don't approximate. You say 1 by 9 and you did do 225. So this is perfect. 225 divided by 1 by 9. That is 225 into 9. That will be 225. It will be electrical degrees, right? So what is mechanical degrees into 2 by P? What is the number of poles? 4. So this would be 225 divided by 2, 112.5 mechanical degrees per second square. The answer is B. You have to be very careful with respect to gate questions about what they are asking, and they will always have some wrong or the answers corresponding to whatever mistakes that you can make in the options as well. Is it clear? I'm going to stop the session over here, right? Chalo. Have a good weekend.